Today we will do the equation of progressive wave. For that, you must be aware of the concept of wave. Of course you are if you have been studying it from high school. Well, a wave is formed when there is a disturbance in the medium, right? It's basically propagation of energy. So the best example is the ripple on the surface of water. But when you see the ripple on the surface of water, how exactly the ripples are formed, how exactly that up and down is formed, if you focus on it, it boils down to our fundamental concept called oscillation. Not only just oscillation, a particular type of oscillation. Can you tell me what is that? Yes, it is simple harmonic motion. Simple harmonic motion where simple harmonic motion is just the same way the pendulum bob oscillates about its mean position. Yes, we did this last year. Pendulum bob, it's going to and fro, right? So the maximum displacement is called amplitude, the displacement is called x or y. This is called amplitude, it's maximum displacement from the mean position. Displacement is generally represented by x or y. Then time period, time taken for one particular oscillation, and how is it related to frequency? Time period is reciprocal of frequency. And angular frequency omega, it is number of oscillations, number of cycles in terms of angle covered, correct? So it is angle covered by time taken. Now one more phase phi is nothing but state of vibration. It varies from 0 to 2 pi. Yes, and we also did last year how simple harmonic motion is equivalent to uniform circular motion, from which you derived this equation for simple harmonic motion, y is equal to a sine omega t. Remember, omega is equal to 2 pi f, or omega is also equal to 2 pi by t, right? Okay, now yes, coming back to the wave. So of course we are talking about mechanical waves, where a medium is required for propagation of a wave. We can take example of waves, ripples in water, or wave in a rope, right? Okay, all these, when it comes to wave, we talk about a wavelength. Okay, before that, let's represent simple harmonic motion in terms of a graph. In the form of a graph, I am representing the displacement of a particle from its mean position as a function of time. In this, we did this last year. The graph is similar to, it's actually same as the graph of a sine function or a cos function. So since it is time versus displacement, at origin I have time t equal to 0. If you imagine a particle at mean position, see, displacement is 0 at time t equal to 0. In the next instance of time, its displacement starts increasing. It will have maximum displacement, amplitude from here to here. Then it comes back to its mean position, goes to another extreme, amplitude on the other side, and again comes back to mean position. So this is equivalent to one complete oscillation. This is called one complete oscillation. So remember, this is only the displacement of the particle with respect to time. Okay, this is not the particle is moving. Particle is in its place. It's only going above the water level. If you imagine one water molecule, it's going above the water level, coming down to the surface level, then again going down and coming back. In the meanwhile, it transfers some energy to the neighboring particle, right? Neighboring particle also starts oscillating, right? That's how wave travels from one position to one point to another. But the particles of the medium do not travel. So this way, displacement versus time graph represents how one single particle of the wave is oscillating in its position. So in this, what is this entity from the origin to the end of the cycle? Since it's a time axis, it is nothing but one time period. Okay, so what is, in terms of angle, what is the angle covered? In terms of simple harmonic motion, the angle covered will be 2 pi, right? It is one complete oscillation. Yes. Now we can also represent a wave, progressive wave, in terms of displacement versus distance. See here what is happening. Wave is starting, okay, and it is going along the positive x-axis. So here the wave is moving. We are having all the particles one beside another. Though I am marking bit far apart, no, actually they need to be too close to each other so that they can take up energy from the neighboring molecule. So yeah, you can imagine these positions as different points in the course of the wave. Okay, so here when I have a crest and a trough, it actually means the instantaneous positions of different particles of the medium. Like the particle at origin has zero displacement, the next particle has some displacement, next particle has some more displacement. Okay, this particle has here the maximum displacement. Okay, so like this particle has zero displacement, this particle is having displacement in the opposite direction, so on and so forth. So if you take this at t equal to 0, okay, for simplicity probably I can number the particles as 1, this is second particle, third particle, fourth particle, fifth particle. So as the wave moves along the positive x-axis, okay, suppose t equal to some instant of time, what happens now? This is at the mean position. Now particle at the first particle is having some vibration. Okay, probably it can go to the positive extreme, right? When it goes to the positive extreme, the next particle will come back from extreme position to mean position, right? The third particle which was in the mean position now should move on to the extreme position on the other negative extreme. The fourth particle, when it was at negative extreme, now coming back to mean position, right? So like this. In the next, again the particle which had gone from mean position to extreme, now it is time for it to come down to mean position. The second which was already in the mean position, for this it is time to go to the other extreme. The third one which was in the negative, okay, yes, if I mark this it's better to understand. Yeah, the third which was already in the negative extreme, now it is time for it to come to mean position. right? Now which was in the mean position, okay, here, which was in the mean position, now it is going ahead to, yes, so it goes on. So this is T2, T3. Now tell me, mean to extreme, mean position to extreme position, extreme position to mean position. Now from mean position to next extreme position, right? See, first particle, we are talking about first particle. Second particle, extreme position to mean, mean position to negative extreme to mean position. So this goes on. Can you guess what might be T1, T2, T3? If total time period is the time taken for the particle to complete one cycle, the time taken to go to a positive extreme or from positive extreme to mean position must be 1/4 of its time period. So I can write it down as T/4. This from origin to extreme, extreme, from extreme to back to mean position, from origin to positive extreme to mean position. So it has completed half of its journey. That means half of the time period. Here mean position to extreme, extreme to back to the mean, from mean position to negative extreme. So it has completed 3/4 of its journey, 3T/4. So when it completes one full oscillation, how the first particle looks like. The first particle, why is it 1? It is still the first particle. Yeah, this is still the first particle. Yes, now it's back from negative extreme to mean position. And the second, right, the second, which was the second particle which was in the positive extreme, now again has come back to positive. So now the wave has reset. So this wave has reset at a particular time interval. What is the time interval? That time interval is the time period. Wave resets, or what we can write, position of, not the wave, position of a particular particle, right? Position of a particle, what happens? It resets after time period capital T. So time taken is capital T. Okay, now so in this course the phase angle it has completed is 2 pi, right? Okay, now yes, by the way, this is actually not the second particle, just for a reference. Okay, particle number 2 I have. There are millions of particles in between this position and this position, of course. So it is just for a reference. I have taken particle number 2. That's all. Okay. Now similarly, we can take a rope. Next, there is a wave pulse generated. Okay. In the second instance, this wave pulse comes here. The second particle takes up this energy, and the third instance, what happens? This has positive, this first particle had positive extreme, same thing happens again, right? Yeah. Okay, now here it's mean position. Then I'm telling you how a wave pulse moves. This is at time t equal to 0. This is time t equal to t1. Okay, next this comes back to mean, but the first comes back to where this is mean to extreme to mean, mean to negative extreme to again mean. The second one, which was there at mean position, now has gone to positive extreme. Now, right, it's the negative extreme. So yeah, now it's again, and the next particle will go. So if you take this, okay, the wave pulse has traveled, okay, from this position to this position, x equal to x, maybe position equal to x. So it has covered a displacement, it has covered a distance of x. Okay, so the pulse has covered a distance x in time, suppose t. Now if I say by the time it has covered distance x, okay, the pulse, the peak which was here has come here, that means it is one complete oscillation, right? So it has covered one complete oscillation. So it has completed one oscillation. So tell me, what is the distance traveled? Distance traveled should be one wavelength, correct? So distance traveled should be one wavelength, lambda. That means time taken should be one time period. So what can you say about velocity? Therefore velocity v is distance traveled by time taken. Now distance traveled, we have set it up to lambda because we have assumed it has taken one time period, or the pulse has covered one complete cycle. So it is, so v is equal to lambda by t, or your famous equation v is equal to reciprocal of t is frequency into lambda. So v is equal to f lambda. So this form is my favorite, personal favorite. I somehow feel nu is so much similar to v that we get confused, so I still stick to f, though in conventionally in wave chapters people tend to use nu. Okay, so I will stick to v is equal to f lambda. Okay, so now we have got the velocity, right? So now keeping this in mind, I think we are good to go ahead with describing progressive wave. Okay, so the progressive wave. Okay, so I'm taking again, let's have this distance versus displacement graph. Okay, now just like how we have set up here, can you see? Yeah, how we have set up here, how we have initiated a wave pulse. We stopped till wave pulse traveled a distance equal to one wavelength, but let it go ahead and set up a full wave. Okay, now my wave pulse was, when I start considering the wave pulse, it was at x equal to 0. Now yeah, now it has propagated ahead. Okay, the trigger is still on, so I have a full wave set up in the rope. Just imagine a rope wiggled by someone on the left hand side continuously. So it is still, we have a nice wave set up here. We know that from crest to crest is lambda, right? Well, be sure, how do you represent crest to crest. It can be lambda, it can be time period. But when is it time period? When x-axis is t. When we are putting displacement versus time graph. When is it lambda? When x-axis is distance. Right. So this is lambda. Okay. Now, just for understanding purpose, again I'm going to set up the particles named: first particle, second, third, fourth, fifth, sixth, seventh, eighth. Okay. 0th, first, second, third, fourth, fifth, sixth, seventh, eighth, 9th, 10th, 11th, 12th, 14th, 15th, 16th, so on. Now, when I see at time t equal to 0, this may not be time t equal to 0. When I see, okay, I take the reference of 0th particle. What is it doing? It is going from mean position. It is at mean position. Okay, this can be this also. Okay, in the next moment. Okay, this also. Okay, this has to be little. Now again 0th, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, so on. 4th, 8th, 12th, so on. Okay, now you see that Mexican wave has set up. See, you can imagine in the football game, in the stadium, or in the cricket, you must have seen, people from one place, people rise the moment the first person rises, second person starts to rise, right? So it goes on. So nice wave is set up. So that's how these guys are behaving. Now, when they are already in the form of a functional wave, okay, 8th, 9th, 10th. Okay, see, 10th guy here is going up and down the same way as the 0th one. Correct? Now, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th. Yeah, 16th, 17th, 18th. 18th guy again is going up and down the same way as 10th guy here. 10th guy is going up and down the same way as the 0th guy. So every person or the particle here, so just imagine a person, every person who is at a distance lambda from each other are going up and down in the same manner. That means if I ask this guy, see, they're all trained, assume they're all trained to be going up and down. People in different position are trained to be going, moving in a particular manner, simple harmonically. They are trained. Now, if I ask this guy, who are you moving like? He will say, I'm having my motion exactly like the 0th guy. If you ask the 18th person, he will say, I'm having my motion, I'm having my oscillation exactly like the 10th guy. So, what do you call these people? 0th, 10th, 18th. What do you call these people? These are in phase. So, the particles are they are in phase. Right? Now, if I set up vibration of 0th guy here, y is equal to a cos omega t. Okay, why not sine? Maybe I'll have to explain a little bit later. Well, both y is equal to a sine omega t and a cos omega t represent simple harmonic motion, but they are a little bit different with respect to their state of vibration. Okay, well, I can explain it right away. At t equal to 0, cos 0 is 1. That means displacement is equal to amplitude. See, since I see maximum amplitude, right, at t equal to 0, well, this is not t equal to 0 because we are taking x, but well, it can be sine as well, no problem. A cos omega t. Then what is happening? Yeah. Now to explain the position of the displacement of 10th guy, I need to include his position as well, not only function of t but position, because different person in general will be having different displacements. Their displacements are not same. So to explain a particle, displacement of a particle in progressive wave in general, I need to have the displacement as function of both time and position. Okay, both time and position. So therefore I will write t comma x is equal to, okay, see this guy here, 10th guy, is having the same kind of oscillation or same displacement as 0th guy. How much second earlier? The distance is, suppose the distance between this is x in general. See, for this is lambda, right? This is lambda. But generally, if you take at any point, suppose I will take in general x, how much time it has taken? It has taken, suppose it has taken a time t. Okay. Now, since the velocity of wave is v, then how much time it has taken for a pulse to come from here to here? It has taken the time, velocity is equal to x by time, distance by time, time is equal to distance by velocity. Correct? Is the time taken to for the
Look at my new type of soup.
Beautiful, very nice. Don't drink it.
I know, pretend.
Taken for the pulse to reach this point, reach x. So the displacement of this particle is same as the displacement of 0th particle. How many seconds earlier? X by v seconds earlier. Therefore, of this position, displacement of this particle here is a cos of omega into, in place of time, t minus x by v. Correct? Now it is a function of position as well as time. So y is equal to t comma x, or we'll simply keep y. A is equal to cos of, what is omega? Omega is equal to 2 pi by t, t minus x by v, cos of, I will just take 2 pi by t inside, okay, minus 2 pi by t into x by v. Now a cos of 2 pi by t is nothing but omega minus, what is t into v here? We have just established that relation, velocity of v is equal to lambda by t. Correct? T times velocity is nothing but lambda. So I will write 2 pi by lambda into x. Where is this t? T. So this term here is called minus kx. Okay, for a particular wave, since wavelength is constant for a particular wave, we are talking about wave in one medium. Since wave in one medium does not change its wavelength. Okay, we can take the wavelength of a wave in one particular medium to be constant. So this constant k is also called wave number, or it is also called propagation constant. Propagation constant, or it is also called angular wave number. Okay, angular wave number actually it represents number of cycles times the angle in terms of phase constant. So k is equal to 2 pi by lambda, whereas omega is equal to 2 pi by t. Okay, yes, here is our equation for progressive wave. Now how y is equal to a cos of omega t minus kx and y is equal to a sine of omega t minus kx are different? Well, these two are different because sine function to become cos function, the argument needs to have a phase difference of pi by 2 radian.